Welcome to GIS 215. This PowerPoint goes over an overview of Esri data formats. These are GIS data formats or geographic information that are commonly used to work with using ArcGIS Desktop and other Esri products. There are many GIS data formats. These particular data formats are proprietary Esri data formats that are built from the ground up to work with their products and have been over time. Know that there are many other open data formats that we'll be getting into later in this semester. But if you're working in the Esri world, these are the common data formats you're likely to see and work with. We'll cover coverages, shapefiles, and geodatabases in depth. I'm still a little under the weather, so please forgive me for the clearing of the throat and possible coughing. I hope that you can get through this. ArcGIS Desktop has a great help online. It's referred to as ArcGIS Resources often, so you can go there to get a lot of help. And we'll also be referring back to several sections of their geodata section of their online help. So you'll see some links to this section in Moodle. Please make sure and read through those links. That's your required reading for this week. And I'll be referring to them some during this discussion. So as a reminder from the introductory PowerPoint we did, geographic data models are an abstraction of the real world. They're how we store real world information in a computer by way of storing geometries or shapes like points, lines, and polygons, and the attributes that describe those points, lines, and polygons. These geographic data models are data objects that support map display, query, editing, and analysis. If you think about it, these are some of the basic things that we do with the GIS. We make maps, we query and analyze our data, we edit our data. So our geographic information, the data that we use, has to support these kind of things. A book I used to teach out of for years by Paul Bolstad gave this definition. A data model may be defined as the objects in a spatial database plus the relationships among them. That's an important definition when we get to the geodatabase and you see the Esri definition of the geodatabase. It'll look a lot like this. It's not only the objects in the database, points, lines, and polygons that represent things like trees or buildings or rivers. It's not only those objects, but it's also how we model the relationships between and among different real-world features modeled as objects in our spatial database. So Esri uses the term geodata to describe data models and data formats. So from the help, you can read that geodata is information about geographic locations that is stored in a format that can be used with a geographic information system. This geodata can be stored in a database, a geodatabase, shapefile, coverage, raster images, DBF tables, Excel spreadsheets, as well as some other formats. We'll see how geodata is stored in open data formats like XML later in the class. It's worth noting that this geodata, these data formats, this spatial data, you hear it referred to in a lot of different ways. We call it GIS data or geographic data or geographic information sometimes. We also call it spatial data. Forever we've been referring to all this data as layers in our GIS. So we overlay information into GIS and that information is stored in some kind of geographic data format. So we talked a little bit about the basic categories of data models. vector versus raster. And I'm going to ask that you refer back to these support pages to refresh yourself on some of the basics of vector versus raster data. You'll want to remember that vector data is best suited for modeling things out in the real world that are discrete in nature, things that have a very definite starting and stopping point, something like a building or a manhole. We model these things with a series of points, lines, and polygons, and we tie attributes or descriptive information about these points, lines, and polygons to the points, lines, and polygons. We also have raster data, and of course that raster data is represented by a gridded structure of cells where each cell has the exact same dimensions. The data stored in raster formats can be thematic data that is also similar to in that it is discrete in nature, like much of our vector data. This kind of data represents land use or soils. But we also store real-world kind of phenomena that are continuous in nature in raster data sets. So things like temperature, elevation, other spectral data, precipitation. These are other types of data we store in a raster data set. Raster data sets are suited well to analysis and modeling continuous data. We can also store things like pictures or scanned maps as well. So this example here is a raster surface map that represents elevation, the white areas being higher elevations and the green areas being lower elevations. We think of this as continuous in nature. There's also a classified image here of discrete type data representing land use, where blue is water, the gray is urban developed, and the yellow is bare ground. Okay, so the major data formats that work with ArcGIS. We're going to start discussing the coverage, then we'll talk about shapefiles and geodatabases. These are the major types of data that you can view in ArcGIS. There are, of course, others. You can view CAD data, and you can view other raster formats that we're not getting into right now, and also view data stored in text files and Excel files. These are the major vector data sources, and the one that we'll start with as a coverage is the oldest data format native to working in the Esri environment. We used coverages back in the day when the software was called ArcInfo, and it was all command line driven, well before it even ran on Windows computers. And this was in the days before Windows 95 and Windows NT. We ran the software on Unix workstations and used coverages to store our geographic information. From there, we'll move to the shapefiles and then the geodatabases. There are, of course, other ArcGIS supported data formats. You can consume many different mapping services via the World Wide Web, web mapping services, web feature services, and web coverage services, or geographic information streamed across the web into ArcMap. This data is stored on another computer out on the web, some server somewhere. CAD data I mentioned. You'll see lots of CAD data later in this class. Excel files and CSV files, as well as raster images and other types of databases. Okay, so the coverage data model. This was Esri's data model in their first commercial GIS software that was called ArcInfo. It was released in the early 80s, around 1981. Prior to that, Jack Dangerman had started Esri. There were landscape architects and planners, and they were building the software to better do their jobs of planning and building and working with the real world. And so after a while, they started to sell the software. So it was referred to as a second generation data model. The real first generation was CAD. CAD was around before this coverage data model. However, this coverage data model was the first geo-relational data model. And what geo-relational means is that the spatial data was combined with database information referred to as attributes that describe that spatial data. So this was different than CAD data, that first generational model. CAD data didn't store the attribute component, the database information, the tabular component. It did store the spatial data, but not attribute data. In addition, this geo-relational data model was able to store topological relationships between vector features. So you could determine the connectivity of features, the adjacency or contiguity of features. So topology is the spatial relationship of features. It's how in a GIS we manage those spatial relationships, and is oftentimes built into the data model, and it was certainly built into the coverage data model. It was a very powerful, first of its kind of thing. So this is what a PC ArcInfo coverage looked like. You see these yellow icons of kind of layered information. This is what they looked like. And this was a little bit more common. This was the ArcInfo coverage, and it looked like this. So understand that this is looking at it in our catalog, where you've got this symbol with two yellow icons in the back with this polygon on top. The ArcInfo coverage was made up of multiple feature classes. So you can see the Hydro coverage had an arc feature class, labels, nodes, polygons, and ticks. This was a very strict enforcement of how data was built, in that you couldn't build polygons without first building arcs. So what you would do is you would digitize lines that enclosed, and when they enclosed, you'd issue a command that generated polygons from them. The nodes were how lines connected together. Labels were how you tied attributes to a polygon, and the ticks were registration points around the extent of the coverage. So this coverage was made up of these feature classes. With the coverage, the important thing to understand is that all of the feature classes were topologically related in that they were connected. The arcs connected to the nodes, and the polygons were generated from the arcs. So the multiple feature classes were connected. Another really important thing to know about the coverage, and this is really with all the GIS data formats. With ArcGIS Desktop, we have a file management tool for our spatial data called ArcCatalog. And in ArcCatalog, a GIS layer like a coverage looks like this. And you can select a polygon and preview it. However, this GIS data format, if you look at it in your File Explorer, what used to be called Windows Explorer, through your Windows operating system, this tool here, you'll see a set of folders with the same name as these coverages, and these folders hold files that are engineered and programmed to store this GIS data. For every folder on a computer that had some coverages in it, we referred to that folder as a workspace. And every folder or workspace that had coverages in them had one info folder. That info folder is where all the attributes were stored for all of the coverages in your Tomasi workspace here. So The GIS system in the background does a lot of managing of files for you, and you should never mess around with these in Windows Explorer. You should always use ArcCatalog to copy and paste files and manage your GIS files. So a really simple rule is if you're working with non-GIS data, things like Excel spreadsheets or zip files or PDF files, you should be working in Windows Explorer. If you're working with GIS data, coverages, shapefiles, geodatabase feature classes, then you should be working in ArcCatalog. And we're going to demonstrate this later, and it should make a lot of sense when I show it to you using the software. Another important thing to think about with this ArcInfo coverage, the info part, ArcInfo. The software used to be called ArcInfo, and notice you've got this info folder here. What's up with that info? Info was a database management system that Esri adopted and programmed their coverage into being stored in this database management system. So this was back in the days when database management systems did not store spatial data natively. These days, many of the major database management systems, like Oracle and SQL Server, store spatial data types natively in the database. In the older days, database management systems like Info and like Microsoft Access and like SQL Server stored information like text, numbers, dates. Those were the data types that these database management systems were capable of storing. Many databases these days still only store that kind of information. What makes GIS databases special is that they also store geometries and coordinates that define these points, lines, and polygons. So before we go any further, let's talk briefly about feature classes. Feature class is a common term you'll see when discussing any data formats, especially in the Esri world. Coverages and geodatabases contain feature classes, while you may see a shapefile sometimes referred to as a single feature class. So what's a feature class? We think of a feature class as being a collection of similar real-world objects that share the same geometry and the same set of attributes. So in a GIS, this is a lot like what we've always called layers. So layers, again, is a really generic term, and feature class is kind of an Esri-centric term, although you see it used in other places now too. So a feature class is a lot like a layer. It's a set of real-world things that are alike and they share the same type of geometry. So examples of a feature class might be a feature class of trees in a park. So all of the trees are similar objects. They're all trees. A feature class, you don't mix trees and manholes because they're not the same kind of things. And so this feature class of trees has a common set of attributes. For every tree, you've got a name, a height, maybe a diameter at breast height, and a condition. So they have a common set of attributes, and they're all points. So within a feature class, everything has the same geometry, a similar set of attributes, and are similar real-world things. Alright, so feature classes and coverages. We saw how feature classes in the coverage that we looked at, there were text, nodes, labels, arcs, and polygons. So there is more than one feature class required to define features in a coverage. The line and polygon feature classes both exist in a coverage representing polygon features. So if you have polygon features, you have line and polygon feature classes, and that's because there was no tools to build polygons. You had tools to build lines, and when you finished building enclosed lines, you would issue a command that generated the polygons. Polygon features will also have label points, and every coverage will have a feature class containing tick points that represent real-world coordinates and allow us to reference our coverages to the real world. It's important to note the spatial tabular link between the geometries, the point signs and polygons, and the tabular information in the table that describes those point signs and polygons. These are true for most any geographic data format, not just coverages, but it's important to understand that features and attributes typically have a one-to-one relationship. For every one, in this example, for every one road, there is one record in the table that keeps up with the coordinates and one record in another table that keeps up with the attributes. ArcGIS for Desktop maintains a link between the feature and the attribute record through a unique identifier that's assigned to each feature. This is the feature sequence number. It's an ID. In some types of data formats, you'll see it referred to as FID for feature ID. Sometimes you'll see it as object ID. The important thing to know is that it's an ID the system keeps up with and manages and uses to maintain that relationship between the record in the attribute table here and which line on this map it refers to. One of the big reasons the coverage was such a powerful data format was the fact that there was a mechanism to manage topology in the coverage. So the coverage is the oldest data format used in Esri, but it was the dominant data format for almost 20 years. So you'll still find data out in the coverage format, and it's important to understand how this worked and compare it to how things work today. So as we mentioned, topology allows us to perform spatial analysis and determine connectivity, adjacency, containment, as well as things like determine the area length and perimeter of features. Topology also helps us to ensure that features are properly connected and built during an edit session. There were tools in the old ArcInfo and the coverage that allowed you to find any lines that were not connected like they should be, where there were gaps in the data. Topology is really just a branch of planar geometry applied to GIS. We'll talk more about topology later in the semester when we go in depth with looking at topology in the geodatabase. With the coverage, the important thing to understand about topology is that topology was stored in the attribute tables. The lines that were connected to lines and the polygons to the right and the left of other polygons were all kept in the attribute tables. This was a great way of doing it back then, but is not the best way of doing it today. Back then, we read from disk often. If you needed to find out information, you would go, your computer software, your tool would go look in a table and look up some information and then return it to you. In this day and age, computers have really just evolved past needing to read from disk all the time. A lot of things nowadays happen in the RAM in real time. So back then, this was a revolutionary way of keeping up with topology, but today it's not done this way. Another important thing is that the geometry shapes were built using shared topology. What that means is that the lines between two polygons were only stored in the database one time. This was really done to reduce storage space, but it caused very strict implementation of topology and meant you couldn't do some things like have overlapping polygons and have donut holes in polygons. So all these spatial relationships, the topology is created and stored in tables was created this way using a couple of different commands, the build and the clean commands specifically. You can learn a little bit more about coverage topology by reading in the ArcGIS resources. And we'll learn about geodatabase topology later in the course. So it's worth pointing out these tables to you. These are our coverage info tables, the tables that store the attributes. And this is a good time to mention the difference between system fields and user-defined fields. Each one of these geographic data formats that we look at today, when they're created, certain system fields are defined that the system uses to keep up with different things about the data. In the coverage, you had a lot of different fields. You had an FID field for the feature ID. You had a shape field that tied to another table where the actual coordinates were stored. And then you had a from node and a to node poly, depending on what kind of feature class we're talking about. This is a line feature class, a line, a left poly and a right poly, and a length. And on polygons, you had an area and a perimeter. And so when you built new lines, created new data by digitizing, the beginning node was the from node, and the to node was the node that you went to. So every time you created a new set of lines, the from and the to nodes were defined in the table. This gave the lines direction. And if you think about modeling transportation networks or utility networks, knowing the direction of a line for a sewer network is a good thing. In the tables, since we built polygons from connected lines, the polygon to the left and to the right of a line was also stored, as well as the length of lines. And here the area and perimeter. So if you wanted to know what polygon was beside another polygon, or what lines were connected to trace a bus route through a road network, you had to know. You would query the table, and it would come in here and it would determine what nodes are connected, so what lines are connected, or what polygons are to the right and the left. So when you asked a question of the software and of the GIS, it would come to this table and try to find the connectivity of things. So these are system fields. Now, you'll also should know that user-defined fields are very important. With this roads layer, some other things we might want to know about the roads are things like the name of the road, maybe the miles per hour on the road, or possibly the number of lanes or the surface, whether it's concrete, asphalt, and dirt. So those are the user kind of defined things that users input and maintain, while the system is keeping up with all this other stuff. Okay, so coverages were great. Times changed though. So why aren't we still using coverages? Well, like I mentioned, the way it implemented topology was great at the time, but computers evolved. Computers are much faster. Things happen real time in the random access portion of the random access memory, or RAM portion of the computer. So things changed. So some of the disadvantages of the way it used to be done is that features were generic points, lines, and polygons. What that means is that a line that represented a road in a coverage format had the same kind of behavior as a line for a river. That's going to make a little bit more sense to you when we look at how the geodatabase models behavior of features, where you can actually attach more behavior to a line in a database so that it does more things like a river does than a road does. And we'll see that. Also, topological integrity was strictly enforced. If you had a line that went across a polygon, the polygon would have to be split. You couldn't have overlapping polygons. Also, as I mentioned, no donut holes. With the coverage data format, large data sets had to be broken into smaller grids as well. And they dropped support for editing this data format long ago in ArcGIS. And that's fine. If you ever end up coming across a coverage file, you need to just convert it to a different format, a more current format like a shapefile or a geodatabase feature class. All right, so on to shapefiles. Shapefiles have become kind of the de facto data transfer standard. So if you go to almost any county GIS site, you'll see their data available to be downloaded in shapefile format. So this data format was introduced back when Esri took its first stab at a Windows GUI-based GIS software called ArcView 2 in the early 90s. The shapefile stores non-topological geometry and attribute information. So the shapefile didn't allow for storing of topological information in the tables like the coverage did. It also was referred to as kind of a single feature class kind of thing. So where in the coverage you could have polygons, nodes, and lines, shapefiles only have either points or lines or polygons. The geometry was stored as a shape or a set of vector coordinates, and the attributes were stored in a DBase file. So DBase, a lot like the old info database that Esri adopted, the DBase format file was not an Esri thing. It was another database file that they adopted and built their shapefile format around. Another great thing about shapefiles is that they allowed us to have overlapping and non-contiguous geometries or polygons. Also, another important thing to understand about shapefiles is that shapefiles went away from that shared topology model where the line between two polygons was stored in the database once. Now, there's a separate line in the database that is part of the definition of each polygon, say polygon A and its adjacent polygon B. There's two lines. They're directly on top of each other. They're essentially the same line stored in the database twice. And the term for this kind of topology or the way we share, or the way features, connected features between adjacent polygons are managed is coincident. So two lines between these polygons, if they're essentially the same line or what's within what we call the cluster tolerance, they are considered coincident. So while a shapefile must be considered as a whole, a shapefile is actually a set of files. So when you create a new shapefile in ArcGIS, in the background, at least three files are created. There's a .shp file created. This is the file that stores the geometry. There's a .dbf file created, or a database file that stores the attribute information about the features. And then the way that the shapefile manages keeping up with which record in that attribute table is associated with which point, line, or polygon is the SHX file. That's a file that indexes between the two, the spatial data and the tabular data, and keeps them in sync. So the SHP stores the spatial data, the DBF stores the attribute data, and this SHX ties the two together. You'll often see many optional additional files. When different things happen to the shapefile as you work with it with GIS, you end up with SBN and SBX files that are indexes of features. You'll also find FBN and FBX, and these are other types of indexes. You may see a PRJ file. This is the file that stores the coordinate system information. That's a really important file. You want it to have a PRJ file. If you define the projection, that file gets created. And some other files. So if you look at the two, if you look at a shapefile in our catalog and you look at it in Windows Explorer, This is the difference that you'll see. Just like the coverage is not well managed by our operating system management, file management tool, the File Explorer, shapefiles aren't either. So if you look here, this streets.shp is actually made up of a bunch of different files. And we're going to go here and look at this using our catalog in Windows Explorer. So over here, my icons in the PowerPoint are a little bit dated. They've changed a little bit, but the colors are still the same. These are the three major data formats we were talking about here. So with our gray cylinder-looking icon, that's a geodatabase. There are different types of geodatabases we'll hit on. That's our coverage. And then you also have your shapefiles here. So your shapefile, even though you see a .shp, your shapefile is made up of more than just the .shp file. In our catalog here, if we preview Buncombe Roads, it looks like that. That's the geography. We can look at the tabular information as well. But if you look over here at Windows Explorer, or the new File Explorer, you'll see that Buncombe Primary Roads, in this folder, there's a bunch of Buncombe Primary Roads. You don't quite need all of those, but you definitely need the SHP, the SHX, and the DBF. The PRJ is very useful as well. So if I were to copy this Buncombe Primary Road shapefile, and I put it on my desktop here, I'm going to paste it there. Notice on my desktop now, I've got that Buncombe Primary Roads. I just made a copy of it. So if I go look at my desktop over here, you'll see that it actually copied all of those files. It didn't just copy the .shp, it copied everything. So you want to make sure to copy your shapefiles using our catalog. That way it gets all the files it needs. Sure, you can do it using Windows Explorer if you copy everything, but don't ever just copy the SHP file. If you do that, your shapefile will not work. So this is the table for shapefiles. And this is not a really very good example, actually. Remember, shapefiles are non-topological. This means they don't automatically keep up with things like area and perimeter. So occasionally you'll see a shapefile table that has area and perimeter in the table. So where do these come from? Likely they're there because this shapefile was once an ArcInfo coverage, and when it got converted to a shapefile, all of the fields come across into the shapefile format. So the important thing to know is that with shapefiles, these fields are never updated automatically. So if I were to take a polygon, this first one, if I were to start editing and split that polygon in half, these area and perimeter fields would not update automatically. There's a lot of people who don't understand that's how it works. There's a tool that you can run on the shapefile that will update those fields. But that's a big disadvantage of a shapefile, is that it doesn't automatically do those kind of things for you. And so those fields can become out of date as you edit and work with your data, and people don't understand that they don't update, and so it causes problems because people get the wrong information when they start modifying the shapes and sizes of their polygons and lines. So with the shapefile, the system-defined fields, there's an FID, a shape field, and an ID field. Those are the only system fields. It doesn't have an area and perimeter field, and so if you add those, or if they end up in it because it was a coverage, you need to make sure to update those using a tool called Calculate Geometry. And you get that tool by right-clicking on the field and going to calculate geometry. And that's something that we'll see later when I demo the exercise. Okay, so shapefile disadvantages. They don't have the ability to store topology. Features are generic with no modeled behavior. If they don't have topology, it seems like they're not useful at all. But relationships, even though these spatial relationships aren't stored in the attribute table, you can determine spatial relationships between features using tools in ArcMap, like the Select by Location tool. There's also a very limited ability to enforce data integrity on shapefiles. So why in the world would you use them at all? Well, a big advantage of shapefiles is that since they've become the de facto data transfer standard, they're also able to be read in almost every GIS software there is. So there's a wide range of GIS and CAD softwares that can all read and write shapefiles. So that's a big reason to use it. It started off as a proprietary data format that only could be used in the Esri world, but over time they opened the data format up so that other software vendors could read and write it, and so it's widely used. Okay, so the final data model we're going to discuss is the geodatabase data model, and we are going to go in much more depth with the geodatabase data model in the coming weeks. This is a short introduction to it. There will be a small amount of the geodatabase on our first test, and then we'll have another test that will really focus on the geodatabase. So it was introduced in ArcGIS at version 8, early 2000s. This is where we start storing geographic data in an actual relational database. We termed it object relational because it also stores things like relationships and between features. So the geodatabase or geographic database is a container for storing our spatial and attribute data as well as the relationships that exist among them. There are several types of geodatabases. The first geodatabase ever released was the personal geodatabase, which is number 2 in this slide. The personal geodatabase stored geographic data in an access database, and it had a limit of a 2 gigabyte file size. Since then, Esri has released the file geodatabase, and the file geodatabase is recommended to be used instead of the personal geodatabase. You won't see many personal geodatabases, and you should never create one. You should always work with a file geodatabase unless you're working with number 3, the ArcSDE geodatabases. So file geodatabases are stored as a set of folders in a file system, and each data set can scale up to 1 terabyte in size. File geodatabases are primarily used when an individual person, single user, wants to create and manage and work with a geodatabase. They can be built with any license level of ArcGIS, the basic, the standard, or the advanced license levels. It's kind of a basic desktop individual use kind of database. Very powerful. The ArcSDE databases, which we don't cover much in this course, are stored in a relational database management system like Oracle, SQL Server, DB2, or Informix. These databases require that you have a higher license level of ArcGIS. You have to have a standard or an advanced license level. And you also have to license the database management system like SQL Server to store your data in. These databases are useful for organizations that have many users that want to interact with one single database at the same time and edit and maintain and work with the data. A good example of an organization that uses ArcSDE geodatabases would be Buncombe County, where they have 6 different people who edit the parcel layer daily, a couple of people that keep the roads data set up to date, and many different users that pull from and use the database in real time at the same time. So these ArcSDE geodatabases are probably more commonly referred to as enterprise geodatabases these days. You'll also see the term multi-user geodatabase. The SDE reference, ArcSDE, refers to the Spatial Database Engine, which is a technology that allowed the Esri ArcGIS desktop world to connect to third-party database management systems like Oracle and SQL Server. Again, it's a higher license level. A higher license level is required, and there's a whole other level of complexity as far as managing an Oracle or a SQL Server database and multiple users and permissions on different levels of layers and features within the database. So again, the personal geodatabase is not recommended anymore. The file geodatabase is for basic data storage and use in the Esri world. If you need multiple users and higher capacity, you can work within the SDE technology, multi-use enterprise geodatabases, of which there are 3 different versions of them: desktop, workgroup, and enterprise. All of these increase with the capacity or size of the database and the number of users as well. So this is what a geodatabase looks like. Inside of a geodatabase, you can have standalone feature classes like the center lines and the census blocks. You can have non-spatial tables that don't have geometries associated with them. So feature classes and non-spatial tables. In addition, feature classes can be stored and organized inside of a feature data set. By putting feature classes inside of feature data sets, it allows you to model advanced functionality like connectivity. You can model networks and topologies and some advanced types of real-world behaviors by managing your feature classes inside of a feature data set. All feature classes in a feature data set must have the same coordinate system, whereas feature classes outside of feature data sets, you can have different coordinate systems. This is the basic geodatabase structure you'll see. And then these are some other geodatabase elements. We'll see raster catalogs and data sets, relationship classes, and topologies this semester, probably annotation as well. Some of these additional elements require higher license levels or extensions of the software to work with them, like topology is a higher license level, and some parts of annotation are. You can certainly store annotation with a basic license level, but to do things like feature-linked annotation, it's a higher license level kind of thing. So we'll see some of these things, topology, relationship classes, some of this raster stuff. So the geodatabase, you might notice, is the one data format we've been talking about that not only does it store vector data, but you can also put raster data in the geodatabase. There's a comparison of geodatabase types here, and again, we stick with the desktop file geodatabases in this class, but I'll let you review that. Personal geodatabases have an MDB extension. File geodatabases have a GDB extension, and that slide is incorrect. Geodatabase tables, the system fields are object ID, shape, and you get an area, a shape length, which for Gnosis is a polygon feature class. In a geodatabase table, the shape length field is the perimeter of a polygon. The shape area field is the area of a polygon. If you have a line feature class, the shape length field is the length of the line. These fields are stored with the units of the coordinate system, So this data happened to be stored in state plane feet, and so this is perimeter in feet and shape area in square feet. You may see meters, and you may even see degrees, which can be a little confusing. We'll see an example of that. So a big advantage to working with the geodatabase is the shape length and shape area fields are automatically updated as the shape and size of features and geometries change. So that in and of itself is a great reason to use a geodatabases. If you're working in the ArcGIS world, geodatabases work wonderfully. If you're working outside of the ArcGIS world, geodatabases aren't as widely supported. Here's an example of some enterprise geodatabases. Again, we won't be covering these, but they're connected to databases on servers. So typically the database might not even be stored on your own computer. You connect to it, you have to have a username and a password and permissions to access the database. So I want to give a quick look here at the databases and how they look in our catalog here compared to how they look in Windows Explorer. So notice that our coverage here, although it looks like a coverage in our catalog, that coverage is actually that folder and this folder together in Windows Explorer. If you want to copy or manage a coverage, always do that in our catalog. The file geodatabase, the .gdb, is this folder here with a bunch of binary files in it. The operating system, Windows, doesn't understand the geodatabase that well. It really works well in your GIS software. So you don't ever want to mess around with this folder with the .gdb extension in the File Explorer. Sometimes I see people saving shape files into this folder or their map documents into this folder. Don't ever save anything into that folder. As you do things to your geodatabase feature classes, as you edit them and analyze them, these files are changing and updating in real time, and you don't want to be messing around in here. If by accident you came in here and you deleted one of these files, you would likely never open the geodatabase again. So stay away from your GDB folders that are your file geodatabases outside of ArcGIS. Your MDB file, your personal geodatabase, I could double click this MDB file and it would open in Microsoft Access, but it wouldn't give us the true GIS functionality. So really you're supposed to only work with your personal geodatabases inside of ArcCatalog and ArcMap as well. And in reality, you probably will not be using personal geodatabases. And you also see the primary roads and the Greenville floodway shapefiles, and those are these files in Windows Explorer. So that's our PowerPoint discussion for today. We're going to have a demonstration of our assignment where you'll see us create some different file formats and look at how the fields, the system-defined fields, are created and managed and what happens with them. And we'll look at a lot of different information about these data formats through an exercise. I did want to show you here one thing though before we go any farther. Remember we said that sometimes if you look at this land use file for Buncombe County, notice the degree, the coordinates down there in decimal degrees. So our units for latitude and longitude are a weird unit. If you took GIS 111 with me, you've heard me talk about this, or 121. The unit of measure for latitude and longitude is a degree. And a degree is hard for us to understand in real world terms. because it changes as it goes around the Earth. A degree is not a uniform unit of measure. The ground distance changes. We all know what a foot is and what a meter is and what an inch is, but what's a degree? Well, if you ever are working with data in decimal degrees and you look at the table that shows the area and the perimeter, if you see these really small numbers, that's square degrees in area. And that's just not something that's easy for humans to understand and to work with. So typically we try not to look at those kind of values when you're looking at data that's in latitude and longitude. That's a good reason to store your data in state plane feet or UTM meters or some other coordinate system that has coordinates or units of feet or meters. Okay, so if you have any questions, please email, and we'll be moving on to an exercise from here. Thank you.